Welcome to Basic Electronics. In the last class, we have seen how a difference amplifier works. We have also seen that its input resistance is relatively small and why that is not desirable. In this class, we will continue with the difference amplifier and consider the effect of resistance mismatch on its common mode rejection performance. We will first consider a simple case in which only one resistance value deviates from its nominal value. After that, we will consider a more general case where all resistances are allowed to vary to the extent given by the tolerance specified by the manufacturer. Okay, let us start. Let us consider this difference amplifier with R3 equal to R1 and R4 equal to R2. And as we have seen before, VO is R2 by R1 times VI2 minus VI1. So in this formula, the output voltage depends only on the differential mode input signal, that is VI2 minus VI1. And in other words, the common mode gain is exactly 0. There is no contribution of the common mode input signal here. That is the ideal world. In reality, what happens is these resistance values are not exact. For example, if you want R1 equal to 1K, it would not be exactly 1K. If you use 1% resistances, then R1 would be anything between 0.99K to 1.01K. So in real life, these resistance values are not exactly what we intend them to be, and therefore R3 and R1 may not be exactly equal. So let us take this simple case where R4 is exactly equal to R2, but R3 is not exactly equal to R1, and let R3 be R1 plus some small delta R. And in this case, our VO also will get modified, and let us see what that is. If you recall, our final expression came from this expression here, and now for R4 we can use R2, and for R3 we can use R1 plus delta R, and then we get this expression here. And now we do some algebra, which of course you need to do, and arrive at this final result. What we do in short is take R1 plus R2 common here from the denominator, and then we end up with 1 plus x in the denominator, where x is delta R over R1 plus R2. Then we use the approximation that 1 over 1 plus x is approximately 1 minus x. And finally, we use these definitions. So after all that algebra, we end up with this expression here for VO. R2 by R1 VD is the differential input mode signal minus x times VC. VC is the common mode input signal. Now this part is the same as before, R2 by R1 times VD, R2 by R1 times VD, but now we have added this common mode part, and therefore the common mode gain is not 0 anymore. From this result, how do we get the differential mode gain and the common mode gain? That is easy. For differential mode gain, we put the common mode input equal to 0, and then the output voltage divided by VD gives us the differential mode gain, that is A sub D, and that in this case is clearly R2 over R1. Similarly, to get the common mode gain, what we do is we put the input differential mode voltage to be 0, that is VD equal to 0, and then take the ratio of VO and VC, and then we will get R2 by R1 times minus x. So that is our common mode gain. Now the minus sign is not so important, so we will only talk about magnitudes. So the magnitude of AC, the common mode gain, is R2 by R1 times x, X is delta R divided by R1 plus R2. This of course is a small number because delta R is small compared to R1 or R2. And AD, the differential mode gain, is R2 by R1, and that of course is the same as before. So clearly AC is much smaller than AD because we have this small pre-multiplier here, and that is good news of course. But the problem is the common mode voltage can be much larger than the differential mode input voltage, and we have already seen an example of that in our bridge circuit. If you recall, VC was 7.5 volts there and VD was 37.5 millivolts. So in that case, clearly VC was much larger compared to VD, and therefore the effect of AC may not be small overall because AC gets multiplied by VC and VC is large. Here is the summary. The common mode gain is X times R2 by R1, where X is delta R divided by R1 plus R2. And remember, this delta R came from R3, which was assumed to be R1 plus delta R. The differential mode gain is R2 by R1, as we already seen. And now let us take a numerical example. We will take the same common mode input voltage and differential mode voltage as the bridge circuit example. So our common mode voltage is 7.5 volts and the differential mode voltage is 0.0375 volts or 37.5 millivolts. So these serve as the input to our circuit, VI1 and VI2, and they are coming from a circuit like the bridge circuit we have seen earlier. Let us take R1 as 1K and R2 as 10K. So the gain of our difference amplifier is R2 by R1. So it would be 10K by 1K, that is 10. What is X? X is delta R divided by R1 plus R2. Delta R is, let's say, 1% of R1, which is 0.01K, and R1 plus R2 is 1K plus 10K or 11K. So this X turns out to be 0.00091. So the common mode gain AC is X times R2 by R1 there. So that multiplied by 10K by 1K or 0.0091. AD, the differential mode gain, is R2 by R1 or 10. Clearly this AC is very small compared to AD. Now let us look at the actual output voltage, the common mode part of the output voltage and the differential mode part of the output voltage. Here is the common mode part, which is AC times VC, and that is 0.0091 times 7.5 or 0.068 volts, 68 millivolts. Let's look at VOD now, the differential mode part of the output voltage. That is AD times VD. So that is 10 times 0.0375, that is our VD, or 0.375 volts. So we see that this spurious common mode contribution is substantial. So this is like 0.07, something like 1/5 of the differential mode output voltage. So it can give rise to errors. And if we measure VO, let's say we get VO as 100 millivolts. What do we conclude? We will conclude that our VD is actually VO by AD or 100 millivolts by 10 or 10 millivolts. In reality, that would not be quite correct because the output also has this contribution from the common mode voltage. and therefore clearly there will be an error which we definitely don't want. So in conclusion, we need a circuit which will drastically reduce the common mode component at the output. Let us now consider the general case in which all of these resistance values are allowed to be inaccurate. We will continue to take R3 to be nominally equal to R1 and R4 to be nominally equal to R2. So let us begin again with our expression for VO and see what happens if we allow all of these resistance values to be inaccurate. In particular, our interest is to get the common mode gain. So let Vi1 be equal to Vi2 equal to Vc, the common mode voltage. So in other words, we are removing the effect of the differential mode input voltage on VO. So with this condition, if we find VO, then our common mode gain will simply be that VO divided by Vc. And if we substitute Vi1 equal to Vi2 equal to Vc here, then VO by Vc, which is equal to A sub C, the common mode gain, turns out to be simply 1 plus R2 over R1 times R4 by R3 plus R4 minus R2 by R1. Let us rewrite this expression as R4 by R3 plus R4 times this bracket, and of course you should verify that these two are actually the same. So far we have not really written these resistances in terms of the inaccuracies or the tolerance values, and we will do that now. Also, we will assume that the op-amp itself is perfect, in the sense it has got CMRR of infinity. So therefore the op-amp does not have any effect on the common mode gain. So how do we incorporate the effect of the tolerance values in the resistances? Using this equation. For example, R1 we can write as the nominal value of R1, which we will denote by R10 times 1 plus x1. And this x represents the effect of the tolerance value. For example, if we are using 1% resistors, then this x1 can be anywhere between minus 0.01 to plus 0.01. And we don't explicitly write this plus minus sign here because that is understood. So with this substitution now, our original expression for AC looks like this. And note that we have not really changed this prefactor. It is the same as before, and we will comment on that later. But in the bracket, we have replaced R2 with R20 times 1 plus x2, R3 with R30 times 1 plus x3, and so on. And our job now is to simplify this expression and arrive at AC in terms of x1, x2, x3, x4. And in doing that, we will find some approximation very useful. For example, if u1 and u2 are small compared to 1, then we can write 1 plus u1 times 1 plus u2 as 1 plus u1 plus u2. And we can do that because this term u1 times u2 is much smaller compared to any of these terms. Similarly, 1 over 1 plus u is approximately 1 minus u if u is small compared to 1. And this is something we have already used earlier, if you recall. So when we go through all of this algebra, we end up with the following relationship. AC equal to R4 by R3 plus R4, this factor, which is the same as this factor here, times x1 minus x2 minus x3 plus x4. So this entire bracket reduces to x1 minus x2 minus x3 plus x4. And it is easy to see why we don't have R2 0 and R1 0 etc. here, because R2 0 by R1 0 is exactly the same as R4 0 by R3 0. So all these just cancels out. It turns out that if we are interested in first order terms in x1, x2, x3, x4, then we don't need to take into account the exact value of R4 by R3 plus R4. We can substitute R4 0 by R3 0 plus R4 0 here without changing the first order expression for AC. So we will do that, and what we do now is take two special cases just to get an idea of the approximate range of AC. Case 1, R1 0 and R2 0 are equal, so these two resistance values are equal. These two resistance values are also equal. So all four resistors are the same, the nominal values are the same. What do we get in this case? In this case we get AC equal to, this is R4 by R4 plus R4 because all resistances are equal, so that is half, and then we get x1 minus x2 minus x3 plus x4. Now in these circuits we are always interested in the worst case value of AC, that means the largest possible magnitude for AC. And when will the largest possible magnitude of AC happen? It will happen, for example, if x2 is negative, x3 is negative, x1 is positive, and x4 is also positive, and all of them have their maximum values in magnitude. So when we consider that, we get half times 4x because all of these will then add up, and that is 2x. So for example, if we use 1% resistances, then this will be 2 times x or 0.02. Case 2 now, in which R1 0 is much smaller than R2 0. So that means this ratio R2 by R1 is much larger than 1. And this of course is a more realistic situation because our difference amplifier has a gain of R2 by R1 and we are likely to make that R2 by R1 large. We continue to use R3 equal to R1 and R4 equal to R2. And therefore if R1 0 is much less than R2 0, what it means is R3 0 is also much less than R4 0. And now let us see what happens to our common mode gain. The common mode gain, the prefactor is R4 0 by R3 0 plus R4 0. We can rewrite that as R4 0 by R3 0 divided by 1 plus R4 0 by R3 0. Now this number is much larger than 1 because of this condition, and therefore this is nearly equal to 1. And once again this bracket has a maximum value of 4 times x, that is the worst case. So therefore in this case the common mode gain would be 4 times x in the worst situation. So again if we have 1% resistances, the common mode gain would be 4 times 0.01 or 0.04. So we see that the common mode gain is not exactly negligible in these circuits, and therefore we need to worry about it. Okay, before we go further, let us do a quick summary. The difference amplifier does give us the desired functionality, namely VO equal to K times V2 minus V1. That is, it amplifies only the difference between the input voltages, and that is exactly what we want for a situation like this. But there are two difficulties. One, its input resistance is not too large, and therefore when we connect the amplifier and the bridge circuit together, it's going to disturb these values, the input values themselves, and that of course is not desirable. Second, its common mode gain is not exactly negligible. What we would like now is to look at a circuit which will address both of these issues, namely the input resistance and CMRR. Here is an improved difference amplifier. What we will do is to understand its functionality first. We will check that it is indeed a difference amplifier, that is, it is amplifying only the difference between VI2 and VI1. And then we will look at in what way it is an improvement over our previous difference amplifier circuit. So let's look at the functionality part first. And let's start with this block. And we realize that it is already familiar to us. It is in fact the difference amplifier circuit that we have been discussing. What is the difference? We had R2 here and R1 here. Now we have R4 here and R3 here. So this R4 and this R4 is the same. This R3 and this R3 is the same. And if you recall, the condition for this circuit to work as a difference amplifier was R2 by R1 equal to R4 by R3. So in this case, what it requires is R4 by R3 is equal to R4 by R3, which is of course true. So therefore this part is simply a difference amplifier, and this VO is then given by R4 by R3 times VO2 minus VO1. And now let us see what the rest of the circuit is doing. Since the op amps are working in the linear region, we can say that V plus and V minus are nearly the same for each of the op amps. And let us see what that implies. It implies that this voltage VA is the same as VI1, and also this voltage VB is the same as VI2. And once we know these VA and VB, we can now get I1, which is VA minus VB divided by R1. And that is therefore the same as VI1 minus VI2 divided by R1. Next, let us use the fact that these op amps A1 and A2, these have large input resistances, and therefore these currents are 0, and therefore this I1 must be the same as the current through this R2 and also this second R2 here. So that is the current path that we expect, and once we know this current path, we can now find VO1 minus VO2. This voltage drop, which is I1 times R2, plus this voltage drop, which is I1 times R1, plus this voltage drop, which is I1 times R2. And we already have I1 here, and we put it all together to get this expression. VO1 minus VO2 is VI1 minus VI2 times this factor here. Once we know VO1 minus VO2, it is easy to get the final output voltage VO, because we have already looked at this and we know the gain of this stage is R4 by R3. So then VO is R4 by R3 times VO2 minus VO1, and now we substitute for VO2 minus VO1 from here and get R4 by R3 times 1 plus 2 R2 by R1 times VI2 minus VI1. So this circuit is indeed a difference amplifier. It is amplifying only the difference between VI2 and VI1, and it turns out to be a famous and very commonly used circuit. It's called the instrumentation amplifier. To conclude, we have seen that the difference amplifier needs to be improved, both in terms of input resistance and common mode rejection capability. We have started looking at another circuit, the instrumentation amplifier. We will continue with this circuit in the next class and see how it provides better performance as compared to the difference amplifier. All right, see you next time.